So, Nikolai, this is where you graph polar graph. So to get a circle on this graph, r, the radius, would have to equal a cosine theta or a sine theta. And if the equation has sine in it, the circle will be on the x-axis. It will be over here. And if r has sine, the circle will be on the y-axis. So over here. There are 4 types of lamisoins. The 4 of them are called interlooped, cardioid, dimpled, or convex. Now, to have a rose on the graph, r must equal a cosine n theta or a sine n theta, and n must be greater than 2 and it must be an integer. If n is odd, then there are n number of petals, and if n is even, then there are 2 n petals, or double. Okay now, Nikolai, my assistant will be teaching you as I have to take a coffee break. See you.
Hello, Nikolai. I am the professor's assistant. I will now be taking over for him. So where did he leave off on?
Oh, he was about to start talking about how to find the area of polar graphs.
Oh, okay. I guess I will take it over from there. Okay, so let's start with the circle which has a center right there. Begin with the area of circle A. Pieces of polar curves look like pieces or sectors of a circle. Area of sector with central angle theta. So this would be your central angle. Let R be the region bounded by the polar graph R equals f theta and the rays theta equals A and theta equals B. Well then, you have to first divide R into n subintervals of equal width, which is the change in theta. So if you were to imagine this, you can imagine it such as, let's say, theta equals B goes like this, and theta equals A goes something like that. And then your R, maybe we have a curve f of theta that goes like that, and your R will be this portion in between right here. Do you understand?
Oh, I get it now.
Okay, so we have to divide R into n subintervals of equal length as I said before. So you can imagine that as, maybe we have to shade this area in. So how can we do that? Well, the way we do that is by drawing lines like that. We need to figure out all of these. How much each one is, like that. This might be a little hard, but you can also think of this as theta equals theta divided by R into n regions with central angle theta. Area of the I region will be approximated by the area of the sector with the central change in theta angle and radius f of theta. So the area of this is equal to, put it right here, 1/2 f theta I squared times change in theta. And thus we can find the area of a polar region given by A equals limit n to infinity and the summation of I from 1 to n 1/2 f theta subscript I squared times change in theta. So the easiest way to consider this is to imagine that the area is being swept out. Like that, like that, like that, like that.
Okay. Thank you so much. Mr. What is your name again?
You can call me, I am Assistant Professor Apple's Carpet.
Oh, thank you so much.
Bye.
Okay, Nikolai, after my assistant Apple Carpet teach you how to find the area of a polar graph, I will teach you to find the area between 2 polar graphs.
What? That's awesome!
Oh, it will be fun to learn. First, I'll give you an example. Here's a problem. Now for example 1, the problem is find the area of the region that lies inside the circle r equals 3 sine theta, and outside the cardioid r equals 1 plus sine theta. So first off, you have to find where the two graphs intersect. So to do that, you would set the two r's equal to each other, like this. And then you would subtract the sine theta from the right side, so you get 2 sine theta equals 1, and divide the 2, so you get sine of theta equals 1/2. And sine of theta equals 1/2 that when theta equals pi over 6 and 5 pi over 6. Now after this, you must graph the two polar graphs. Since r equals 3 sine theta is a circle and it has sine in it, the graph would be on the y-axis, like this.
Cool.
And then you would graph r equals 1 plus sine theta, which is a cardioid, so it looks like this. Hey Nikolai, you know what that looks like?
No, what?
You know what it looks like.
No. What, like a heart?
If you look, maybe if you look at the other way around. But it looks like a butt cheek to me.
You're right, ha ha ha.
Okay, now all joking aside, see as here, the intersections are over here and over here. And now this is pi over 6, and this would be 5 pi over 6. And now you would use the equation, the formula for area, which is, okay, first of all, you must find the area of the circle from pi over 6 to 5 pi over 6. So you would use a formula which would be 1/2 times pi over 6 to 5 pi over 6 of the area of the circle, which is r equals 3 sine theta, and you would square that. So that's only the area of the circle from pi over 6 to 5 pi over 6. And you must subtract that from the cardioid from pi over 6 to 5 pi over 6. So you would do the same formula again, except now the inside r would be different, which would be 1 plus sine theta squared. So then you would get the area. Oh, almost forgot the d theta.
You can't forget d theta.
Yep. And now, once you do that, you would get the area inside the circle, but outside the cardioid, which would be right here. And now since the...
So wait, let me get this straight. This equation right here, is it true that that equation's actually giving me this whole thing?
Yep, you got it right, Nikolai.
Oh, I get it. And then you have to subtract it from this equation right here, which is giving me, which is like this part of it, right?
Yeah.
Which is like this part of it, right?
Yep. Yep.
Cool.
No, aren't I such a good teacher, Nikolai?
Yeah. So what do you do next?
Well, since the bounds are the same, and there's a 1/2 on the outside on both equations, you can just combine them. So since the bounds are the same, and there's that 1/2 on the outside for both equations, you could just combine them. So it would look like this. And the d theta. I forgot that again. And that would be the final answer.
Oh, cool. Now, how would I get the exact answer?
Well, for that, you would need to use a calculator.
Ah. Or I could integrate by hand too, right?
Yeah, you could do that yourself. If you feel like you're brave enough.
Ooh. Thanks.
You're welcome.
Professor, is that your phone?
Oh, wait. Oh, it's my wife. Hello? Oh, hi. Sweetheart. What? Right now? Oh my god, I'm coming right now then. Oh, sorry, Nikolai. I have to go. My wife is just having her baby.
What? No, wait! Call your assistant! Thank you! Hello, Nikolai. I hear the professor's gone, so I'm here to teach you again. Sit down, it's okay. Alright.
Okay, now let me start with example 2. Find the area of the region that lies inside the common areas of the curves r equals cosine 2 theta and r equals a half. Okay, first before I draw the graph, let me just find what the intercepts are. Okay, let's set cosine 2 theta equal to 1/2. Do you know, Nikolai, what r equals 1/2 looks like?
Oh, would it be a circle?
Yeah. Do you know what r equals cosine 2 theta looks like?
Roses.
Yep. So let's set them equal to each other. So because we know we have to find out when cosine 2 theta equals a half, we can just say that we can just find out when cosine equals a half. So cosine equals a half at pi over 3, 5 pi over 3, 7 pi over 3, and 11 pi over 3. Now, by dividing all of these by 2, we get pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Now we can draw the graph. That'll have to do. Let me draw a circle now. Okay, so the intercepts, as we discussed before, are at pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Oh wait, that's not 7 pi over 6. Let me just go back and fix it in a second. Okay, now this graph. Let me just shade in the stuff we're looking for. So we want the area that lies inside both of these, which is right there, including the little slivers. Like the sliver right there that I'm drawing in, shading in. Sorry. Okay, now that I have these, next what I must do is find out how I can do it the easiest way. And the easiest way to do this would be to use symmetry. Now I will use symmetry to find the easiest way to do it. Because we have 4 of these big curves right here, we can do an equation that says 4 times, we draw the little pizza slice, which is what it kind of looks like, equals, 4 of these equal 4 times, once again, 1/2 the integral of negative pi over 6, which is right there, and 2 pi over 6, which is the first intercept, 1/2 squared d theta. As you can see, this is just an area of a circle and can be completed quite easily. Okay, now to find the little slivers, we need to find, let me go to the sliver right here, which you can actually see. To find this sliver right here, so I'm shading in the little sliver of area. To find that sliver, we must find when cosine 2 theta. Sorry about that, I just got the lapse. We have to find when cosine 2 theta equals 0. Let me scroll down for you. Let me write in green, I like this color better. Which occurs at 2 theta equals pi over 2, 3 pi over 2, and 5 pi over 2. And 7 pi over 2. Dividing by 2, we get pi equals pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, so this means that using symmetry, again, we can do 8 times the tiny slivers, which are the ones I have shaded in. Let me scroll down for some more space. That's what they look like, the little tiny slivers. Which is 8 times 1/2 the integral of pi over 6 to pi over 4, which is from here to here. Let me scroll back up so I can show you it on the graph. It is from here, yes, that's pi over 4 right there. So it's that tiny sliver from there to there. Okay, now going back down. Now, as I was saying, it's from pi over 6 to pi over 4, cosine 2 theta squared d theta. So our final area, A, is equal to 2, the integral of negative pi over 6 to pi over 6, 1/2 squared d theta plus 4, integral of pi over 6 to pi over 4, cosine 2 theta squared d theta. And this is our answer, which we can use integration techniques to solve or solve by hand on the calculator. Do you understand, Nikolai?
Yeah.
Good.
Okay, that's all I can teach you. Good luck on your adventure, Nikolai. the part of the park that's supposed to have the treasure. Francois. This is actually in the area that was described, and that's the problem. I went to the professor and did the whole thing out. He taught me all about it, and it's supposed to be here. Oh, watch out! It's pretty muddy. Look, I think it's just past the jungle gym. Go, come on. You see it? Oh, look. I see it. It's treasure! What's this? Treasure! Yeah. We got it! Treasure! Oh, Francois, look! It's a magical calc book.
Oh my god.
With all the ways on how to do calc properly.
Let me see.
It's
so
awesome.
Cool.
Wait, I think I hear somebody knocking upstairs.
Uh-oh.
You hear that? Oh, we better go find out who it is. We'll come back and we'll look at it, alright?
Okay.
See here, I'm the calculus mugger. You steal this? Oh yeah, goody goody.